We are going to start using a simple equations. AV plus BX give you CY plus DZ. In these reactions, what are your reactants? V and X. What are your product? A, B, C, D. We call it stoichiometry coefficient. Okay, so if you look at this plot, x-axis is time. What is your y-axis? The concentration of reactant and product. See the color coding here? This two is your reactant, right? And the bottom two is your product. What this does is actually, if today you let this reaction to occur, you have your initial concentration of your reactant and product. Then you start to monitor the concentration of each species, how it actually evolve. How does the concentration of your reactant evolve? Your reactant start to decrease. The reason it decreases is because it's forming the product. So at the same time, you see your product start to show up. If this thing goes on and on and on and on, okay, after a very, very long time, you reach equilibrium, right? So when you reach equilibrium, the concentration of each species becomes a constant, right? Which means the concentration of your reactant, concentration of your product, they don't change anymore. We call the system reaching its equilibrium. We are going to define something called Q, the reaction quotient. We use the product concentration raised to the C's power, D's power, which is actually its associate coefficient in front of it, divided by the same thing, but you do it with your reactant. Now let's get back to these figures. Is chemical quotient a constant, or the chemical quotient will change with time? Change with time, right? Because the concentration in the beginning is actually changing. Can you actually calculate the chemical quotient at this time point? You can do that, right? So you just need to find out the reactant concentration, product concentration, and plug back to the equation. Then you can get the chemical quotient. And then as time goes by, you can see Q1, Q2, Q3, they will be all different, right? Because the concentration of every species inside your reaction actually changes. But after a certain time, which we know when the system reaches equilibrium, the concentration of your species, they don't change anymore, right? That means your chemical quotient will be a constant. Under that condition, we call the chemical quotient is equals to your equilibrium constant. So equilibrium constant just a very specific cases that the chemical quotient reach equilibrium. From here we know the chemical quotient is going to equals to your equilibrium constant once your system reach equilibrium at a given temperature. So that's the difference between chemical quotient and the equilibrium constant. For all reactions, what you should expect is that the reaction eventually is going to reach equilibrium. Therefore, your reaction always happens in a way that you are going to make your Q equals to your K. This is actually a very important concept. The question you're going to encounter is like this. I give you a Q, I give you a K. Tell me where the reaction is going to move. The simplest case is if the Q is equals to K, then the reaction will not move, right? Because it's already at equilibrium. So it's not moving toward your reactant side. It's not moving toward the product side. It's at equilibrium already. However, if I give you two numbers for your Q and K, and then when you compare them, you realize your Q is smaller than K. Because when we write out a Q, it is always product over reactant. If Q is smaller than K, that means you don't have enough product compared to the equilibrium condition. So the system will push the reaction toward the product direction so you can actually crank up your denominator so that eventually it will equal to your K. If your Q is larger than the K, okay, that means actually you have too much product. You want to bring the product back to your reactant. So the reaction is going to move toward the reactant side. Okay, so this is actually the first type of question you're going to encounter for chapter 12. Then we need to move to the second one. So how do we get the Q or how do we get the K? So we're going to use this one as example. So this is a reaction that the hydrogen interact with your nitrogen to form the amines. So N2 plus 3H2 going to produce 2NH3. So when the system reach equilibrium, we're going to write this double arrow to represent the system has reached equilibrium. You can actually write these things separately. So I can write this one is actually going to equivalent as N2 in the gas form plus H2 in the gas form. That's going to form your 2NH3. Right? We call this as a forward reaction. But for your system to reach equilibrium, that means that you also have things happening in the reverse direction. Assuming these are your elementary steps. Then for your forward reactions, you can actually write out your rate. The rate can be written as forward rate constant K times your N2, which should be 3H2, okay? And then H2 to the third power. You can do the same thing for the rate of reverse reaction. It's going to equal to your rate constant K reverse multiply N3 to the second power. When we say a system reach equilibrium, one very, very key concept you should have is that the forward rate is going to equal to your reverse rate. So at equilibrium, the forward rate is going to equal to your reverse rate. The definition of the equilibrium constant was defined as the rate constant forward over the rate constant reverse. Once you know that's the definition, you want to substitute your Kr and the Kf with this. From here, you know your Kf is going to equal to your Rf divided by your N2 to the first power, H2 to the third power. Here you do the same, you can get your Kr is just equals to the rate of reverse reaction divided by your NH3 squared. Okay, so when you plug in into here, what you're going to get is the rate of the forward reaction divided by your N2, H2 to the third power, reverse rate divided by NH3 to the second power. And then this is going to give you reverse rate times your M2, H2, third power. On the top will be forward rate times NH3 to the second power. So once you have this, we know once you reach equilibrium, your Rf and your Rr, they are actually the same, so they will cancel out. Your Keq is simply equals to NH3 squared N2 first power H2 third power. And then if you look at that, it's actually just like the things we say, right? So when we define your reaction quotient, okay, it's really the product raised to its coefficient divided by the reactant raised to its coefficient. It actually all comes from the concept we have from chapter 11. So this is how we actually connect the equilibrium with kinetics. Kc and Kp, they are all equivalent to the equilibrium constant. Just the unit you use or define is actually a Kc or Kp. Okay, and I'll just give you two examples so you can see the things more clearly. For the following, equilibrium concentration was observed for a process, which is these reactions at a certain temperature, where we know the concentration of each species is equal to a certain number. Calculate the K. The first things when you see this chemical equation, make sure the equation is balanced. Once you know the equation is balanced, then you can actually write out your law of action. So again, product on the top, reaction at the bottom, you always need to raise to the power that associated with the coefficients. Okay, once you have this, the next thing is actually just plug in the concentrations. Then you can actually get the correct answers for your equilibrium constant. So here, if you look at the unit is all molarity, right? So once you see these concentration terms, you know the K you calculate must be Kc. So when are you going to see Kp? So the main difference between this and the previous question is that the unit it provides is not a typical concentration unit we have learned in chapter 10. So here is actually a unit of pressure. ATM, bar, ha, all of things is the unit of pressure. Because you are using pressure to calculate your equilibrium constant, then this is Kp, not Kc anymore. The things that got more interesting or trickier is in your homework. Conversion between Kp and Kc is something you're going to get tested. So how do you convert the Kp into Kc? The concept you should have is the ideal gas law. P is the pressure, V is the volume, N RT, M is number of mole, R is just a constant, T is just temperature. If you move N to the right hand side, then you got this P equals to N over VRT, right? And this will give you a concentration M times R times T. That means if you want to convert the pressure into concentration, the main difference is RT, right? So this is actually the part that you're plugging into the conversion. Let's use this as example. This is the Kp we defined in our second example. Using this one, I can rewrite the things in terms of concentration. I convert this into this, concentration times your RT to the second power. And then you do the same thing for your reactants. So once you do that, I pull out all the concentration terms together. I put all the RT terms together. So once I do that, I know this is going to equals to my Kc. And all the remaining thing is actually just my RT correction terms. To generalize this idea, this is what you should do. Okay, assuming today you have chemical reactions, then assuming you can calculate its Kp and the Kc, and they can correlate with each other with this equation. So your Kp is going to equal to your Kc multiply RT to a certain power. The delta N was calculated by the sum of coefficient of your product minus the sum of your coefficient of your reactant in the gas phase. So let's use this as an example. 2NO gas plus Cl2 gas, that giving you 2NOCl gas. The delta N will be the coefficient of the product in the gas form. In this case, it will be 2 minus the coefficient of your reactant in the gas form. 2 plus 1. That's the 2 less the 1. Your delta N is going to equal to 2 minus 3 equals to negative 1. Therefore, you know your Kp equals to your Kc multiply your RT to the negative 1 power. And then this is going to equals to Kc times 1 over RT, which is actually the same answers you got previously. The very last thing we want to talk about is this page. If today I just do some modification of my chemical reactions, how will I actually change your K values? Okay, assuming today you have a chemical reaction AA plus BB that gives you CC plus DD, and it has its associated equilibrium constant K1. Rule number 1, if today I reverse these reactions, once you reverse these reactions, you actually got a new equilibrium constant. And I want to know how this K2, is related to the original K1. From the things we learned, we know, okay, for this reaction, I can write the K2 is simply equals to product is A to the A's power, B to the B's power, C to the C's power, D to the D's power. For your K1 is actually C to the C's power, D to the D's power, A to the A's power, B to the B's power. So you know K2 is simply equals to the inverse of your K1. So you know if you switch your chemical reaction, then the new equilibrium constant will be the reciprocal numbers of the original equilibrium constant. So that's the first rule that you need to memorize. Rule number 2 is that if I multiply a coefficient to like whole equations, in this case, I just multiply a factor m. The new equilibrium constant K3 is going to equals to C to the C's power times N D to the D's power times N divided by A to the A's power times N B to the B's power times N. And this can be written as C to the C's power, D to the D's power over A to the A's power, B to the B's power to the N's power. This term is just your K1 to the N's power. In other words, if today you just multiply your original equation by a factor of n, then the new equilibrium constant K3 is going to equals to K1 to the nth power. Okay, rule number 3. If today you have a reaction AA that becomes CC, BB that becomes DD, and this have a equilibrium constant K1 and an equilibrium constant K2. If today I adding up, so that I have AA plus BB that give me CC plus DD, then I have a new equilibrium constant K3. And this K3 is going to equals to K1 multiply K2. So these 3 rules, you need to actually memorize it. And then we're going to apply the things we learned right now to one example. This question says, for these specific reactions, I have a rate constant of certain values. And then it wants you to estimate the equilibrium constant of these 3 reactions. When you look at this equation, then you want to compare to your reference equation. The equations that you see here is actually the same, but you multiply 1/2. Then the new equilibrium constant K, let's call this K1, okay, should equal to your original equilibrium constant raised to 1/2 of power. So this actually using the rule number 2 to do this calculation. How about this? How is this related to your given equations? The first thing you should see like is actually this product not become reactant. That means actually the reaction has been flipped. We know when you flip the reactions, it will be actually the reciprocal of the original K. How about the coefficient? You go from 2 to 1. That means you multiply 1/2 again. Means your new K is going to equals to your original K multiplied by 1/2 because you reverse your reactions. So you need to have a negative sign, go with it. Okay, so again, this is actually using the rule number 2, right? And this is a combined rule number 1 and the rule number 2. The very last one is again rule number 2, right? Because you can see the coefficients go from 2 to 3, right? So you know your K is going to equal to your K1 raised to the 2/3 of power.